What's going on, everybody? This is Mr. Diamond, and we're going to be moving into our notes over projections, stereoisomers, conformations, and there's going to be a couple other little minor things in here. Now, I've got my molecule kit. I haven't made any structures for this, but there's a good chance that we're going to need some structures for this video. So if you've got your kit nearby, I would go ahead and recommend that you go ahead and get that close to you. So we're going to be moving on to the second category of isomers. Stereoisomers in particular. As a reminder, those are when the atoms are attached in the same sequence, but their position in space is different. So if I make a really quick, just super basic one, we've got our double bond is what we were looking at before. We said that you had the chance, if I go ahead and put them like this, even though this is 4 carbons attached by single bonds, and then on the second carbon there is a double bond between the second and the third carbon. This and this could both be described by that phrasing, by 4 carbons in a chain where the second and the third carbon are connected by a double bond. Both of this and this can be described by that. And we said that we had to differentiate that because of this double bond. We called it cis-trans, or we called it with an easy configuration. We were focusing on those pi bonds as the major part that allowed them to do that, but our new isomers will not involve double bonds. I mean, they might involve double bonds, but the reason they're isomers is not going to be specifically because of their double bonds. Our new isomers will involve specific positions of attached groups being different. In order to describe this, though, we're going to need ways that we can actually describe things in 3D space, and that's where we're going to be going for most of this video. There are a bunch of methods for this. The dash and wedge method, the Newman projections, Sawhorse projections, Fisher projections. We're going to touch on them as we need. You will probably be required to do all of these at least once during this class, but maybe not all of them during a test. Dash and wedge method is something you've actually probably already seen on some of the problems that we've done, or if you've looked up models online. They showed 3D arrangements of atoms in a more accurate way. Dashes, or the little hatch-marked lines like this, are representing something going into the page in 3D space. And wedges are things pointing outwards. So the example it's giving there is methane. I'm going to go ahead and really quick. I really don't like that this methane molecule has CH4 as the middle, like that whole middle piece is a CH4. That's not how that works. But if I go ahead and make my methane, there are 4 hydrogens attached to a single carbon, and we know from discussing earlier in this year and from last year that that makes a tetrahedral geometry. So we've got our kind of little caltropy shape that looks like this. I make sure all the bonds are connected. So this is our methane molecule. And if you were to actually draw this in 3D space, a lot of people would probably draw something kind of like this. But that's not super accurate because, again, I mean, I can hold it that way, but it gets kind of weird to try to get it to line out that way. It's not going to actually be flat in the page. So instead, what you'll usually do is you'll try to make as much of it as you can flat. So in this case, I'm holding it up here. These lines would just be normal because they're flat. They're two-dimensional. But then these 2 hydrogens right here, I'm really hoping I'm holding that in frame. These 2 hydrogens right here are going into or out of, or depending on the direction you're looking from, for me it's the opposite. So for you guys on the camera, you would write this hydrogen bond coming back here as it's going to be dashed because it's going away from you. And this one's moving towards you, so we would write that as a solid, like, wedged line, a big, like, black kind of trapezoidal shape. And if I kind of hold it like this, you can't exactly see where they are, so we do draw them slightly offset, like we have right here. We have them a little bit offset from each other. And if I kind of angle this just a little bit, you can kind of see where that shape is coming from. These are mostly flat, and then these 2 are coming in at kind of an angle. Newman projections are used to represent conformations of organic substances. So these are going to be a little bit differently. Conformations are arrangements of atoms in a molecule that come from rotation about a sigma bond. And again, a sigma bond, if you remember, is the first bond between any of the substances. The first bond made in any covalent bond is a sigma bond. So in a Newman projection, what you're going to be doing, and I'm going to make, I think this will probably be the molecule we're going to be working with, if I remember my notes good enough correctly. So I'm going to make a butane molecule, at least most of a butane molecule. So what you're going to do is you are going to take whatever carbon it tells you to look down. So the way this will be worded is it'll say like looking from the C3 to the C4 carbon, or in this case this would be the C2 and the C3 carbon, because this is the second, this is the third carbon. So we're going to look down it like we're looking down the bond. The bond is actually going to be angled so you can't see it. It should be hidden by your molecule kit. You're going to indicate the front atom as a dot and the back atom as a circle going around it, so it'll look kind of like the Dr. Manhattan symbol almost going right here. And then you're going to actually, it's now going to matter how we twist and how we turn these things. So after you've indicated your dots, you'll add in some other groups, and there you go. So if you've got ethane, which, let me convert this to ethane really quick. So we're going to add on hydrogens here. If I were to look down the carbon-carbon bond of ethane, I would be able to see that there is, again, I can't see the bond that's right here. I can't actually see this physical bond that's right here, but I can see all of these hydrogens on either sides. And so I would just draw them in the position that I see them in. However, we aren't using dashes or wedges, even though they are tilted slightly inward and slightly outward. You will notice, though, that since this is a sigma bond, we can actually rotate this. There's actually a whole bunch of different ways we could tilt this and we could angle this whenever we're drawing our picture. And that definitely comes up when we have one where we're now talking about the second and the third carbon of a butane molecule. So I'm going to swap out one of my hydrogens, and we're going to put a carbon here. I'm not going to add hydrogens to it just because I'm already spending so much of this video adding hydrogens to things and making shapes. So right now I've got, if I hold it up kind of how we're more familiar with it, I've got 1, 2, 3, 4 carbons, so that's a butane molecule. And we're going to look at the bond between the second and the third carbon. So I'm going to find that bond, and I'm going to turn it so that way that bond is hidden from me. It's behind my little molecule pieces right here. But now we've got a little bit more of a problem. I'm sure you might be wondering, well, wait a minute. Okay, mine, based on how I'm holding it, has like a carbon going up and a carbon going down. Can I have it this way? Or can I have it this way? Or can I have it this way? Like, does it matter where I put the groups if it's not all identical? And the answer, of course, is yes. It does actually matter. However, it doesn't matter in the sense that the molecule will change. Remember, this is all going to be butane. It's all 4 carbons. We're just twisting this single bond. That's not actually changing what the thing is. You're affecting the stability and the energy of the molecule. So when you are putting them as far apart as possible, so I'm going to tilt it now, so if I hold this up, again, I hope this is in frame and kind of well visible here. The bond is hidden that we're actually caring about. In the front group, I've got it going down, and in the back group, I've got my carbon, my CH3 that I haven't added the hydrogens to, going up, which is exactly what we have represented right here. The carbon in the front is going down. That's this piece right here, and the carbon in the back is going up. It's this piece right here, and then the hydrogens are going off at angles from it. We call this an anti-configuration. This is the lowest possible energy you can have. It's when the biggest groups are as far away from each other as they can possibly be. They're 180 degrees away from each other. So this is an anti-configuration. If we were to tilt it and we were to rotate it so that way they are still kind of not overlapping, but they are close to each other. They're pretty close to each other in this case. So if I look down the barrel, I see the one in the back is going up and the one in the front is going off to the side. This is called a gauche projection. It means that the groups are not as far away from each other as possible, but they are still separated, and there's not a tension in the position of the bonds. That will make a little bit more sense later on. So this would be gauche. This would also be gauche. I guess this would also be gauche. All of these would be examples of gauche projections. They're staggered from each other, and they're not as far away from each other as they could possibly be. All of these, well, this one wouldn't. This one would not because they're opposite of each other. But anytime that it's not as far away from each other as possible, it is a gauche projection. Eclipsed projections are when you, instead of having them kind of, you notice that I've always had them making like this 6, you can see all 6 of the bonds. If we instead angle it so that way they are completely overlapping each other. So I have both of the bonds right here, both of the bonds right here, both of the bonds right here. These are the highest energy and the least stable conservations, and they also have the most variety. Eclipsed means that they're occupying the same position on that circle that you've kind of been drawing here. So again, if I hold it, it's kind of, they're all overlapping each other. So this is the worst and the least stable configuration you can have. These are how we would draw them. We would draw them just slightly overlapping each other, so you can kind of still see that there are two distinct ones, but without actually having to like try to draw them overlapping. Now, the two variations on them you have is the first one is like this, where I've got them lined up and I have carbon, hydrogen overlapped. And then the other version of it would be hydrogen overlapped down here, and then the carbons are overlapped up here. So which one of these do you think has the lower stability? And it may be just kind of a guess based on what we've got right now. But if I were to actually add a couple of the things, because remember, this is supposed to be a carbon up here. This is actually going to have a bunch of hydrogens attached to it. So I'm going to go ahead and I'm going to add some hydrogens to this top piece here. And I'm going to add some hydrogens to this bottom piece here. I know I said I wasn't going to, but now I realize it's probably a good idea for me to do it. So if I go this direction, these things are bulky. There's a lot of stuff that's trying to take up space over on this side and this piece right here, but they're kind of far enough away. But if I rotate this up here, and if I twist these a little bit, I can actually get my hydrogens to bump into each other. So that is very close. And hydrogens do not want to be close to each other because they're going to have electron orbitals, and electron orbitals are negative, and those negative orbitals are going to try to repel away from each other. So this is very, very unstable. It will take a lot of energy to keep it in this shape and try to keep these big clunky molecule pieces close to each other. So it will actually get pushed. And this is also going to be for the same reason. It's just not as bad because the hydrogen is a little bit smaller than that. Ideally, they're going to go opposite of each other, and they're going to be staggered, so none of the bonds or none of the atoms are in the same kind of 2D space as each other. So this projection has the biggest groups closer, so that's bad for stability. The groups that are closer together will put strain on the molecule and its structure. Strain is a reduction in stability because of a molecule not being in an ideal shape, basically. There's a bunch of different types of strain. There's torsional strain, steric strain, and angular strain. I'll have the next slide what those are about. But just to give you an idea of what we're talking about energy-wise, so that anti-configuration is really, really low. And then as you rotate it, if you line up the hydrogens with that, you've got your eclipsed that's pretty high. Gauche, when you kind of rotate it back down here, is still a little bit higher than this, but is not super high. And then if you have the big groups overlapping, you will actually have this really, really big spike in energy. There may be a question on the test that asks you to draw an energy curve as you rotate this thing about it. So let's start from like our anti-configuration. As you are rotating it and doing a full rotation of that sigma bond, you can draw what the energy is. And most of the time it will start with, it'll go small, up a little bit, down higher than where it was before, up really big spike, plateau again, middle spike, and then small. I'll do an example of what that looks like on my actual examples when I do them. You'll kind of understand what's going on with it, I hope. So torsional strain is how much a bond will resist twisting into a specific conformation. It comes from the same root word as torque. If you ever heard of like torque in a tire or in a rotational energy, torsional strain comes from that. It's the strain from twisting into a conformation. Steric strain is the problem we were having right here. This is called the steric hindrance. These things are so big, they're physically going to bump into each other if you try to twist them or if they're in the right configuration, and that is not good. So that's going to put a lot of tension in the molecule. And then angular strain is another one that's not super common, and most of our examples won't be really involving it, but that's whenever the actual angle that the geometry or the molecule is held in is not what you would expect the molecule to be in hybridization-wise. So for example, I'm going to go ahead and and I'm going to do, you guys have probably done stuff like this actually already, where you've made molecules that are like, oh, that's not really what you would expect the molecule to make. So if I take and connect my 3 carbons into this triangular ring, we're going to go ahead and try, and let's see if we can do this. So we've got a double bond there. Let's do, I don't actually think this will be possible. Ooh, there we go. Okay, so I have this molecule. It looks rough. It looks like it should not be in a position that's expected to be in. And if you look at this specifically, this carbon right here, this carbon is a part of this 3 ring, and based on what you know from triangles, if it's a triangle made out of 2 of the same bonds, this would be an isosceles triangle, you would expect that the angle for here would have to be something less than 90. These guys, though, because they're double bonds, if you remember back to our geometry lessons in chemistry, we talked about how being with a steric number of 2, because it's connected to one thing here, you would expect this to have a 180-degree difference between its bonds. And if I break this piece right here, that is the angle that it wants to hold. It wants to be in a straight line. It wants to be at 180 degrees away from each other. But by putting it in this position, I'm forcing it to be in a position it does not want to be in. So this would be angular strain. You are making the molecule bend to an angle it does not want to do. So those are the 3 types. It's either twisted in a way it doesn't want to be, it's getting too close to something, or it's at an angle it doesn't want to be. So we'll do an example of this Newman projection. I'll have that as a separate video of this whenever I'm on my actual projector or on my document camera, so you can see what we're talking about there. Sawhorse projections are actually exactly like Newman projections. You're just going to angle them slightly differently. So we had our Newman projection of this, where let's say we have it in our anti-configuration like this. Instead of having it be as circles, you're basically going to just tilt it to the side slightly, and you're going to pretend that this gets stretched really, really far apart from each other. And then you're just going to draw them at an angle of each other. And that's kind of what's happening right here. So here's our anti-configuration from that molecule there. We would have drawn it this way for a Newman projection. We just stretched out that bond. We're still not using dashes and wedges on this one. And you would draw what each of those pieces looks like with a line between them instead of with a circle. I'm just telling you this as it exists. Newman projections are the more common way we're actually going to be using them in class. And then we'll do an example of that one as well. Okay, so that gets us to stereoisomers. I think we're going to stop right there. So that's where I'll cut myself off. I'm going to stop right there. If you have any questions, please shoot me an email. There will be a video below this of me working out the example problems, like this one right here and the one for the Newman projections. Let me know if you have any questions. In the meantime, this is Mr. Diamond signing off. Hope you have a good rest of your day, everybody.